All right, friends, welcome back. Uh, just a couple of sort of housekeeping things. First, happy Star Wars Day. May the Force be with you. May the Fourth be with you. And I guess the proper response is "and also with you," something like that. Um, let's see. I can't find the microphone today, so I'm just going to have to talk loud. If you can't hear me in the back, just let me know. Um, if you've been following along with the syllabus, you know that our first exam opens Friday and closes Monday. Testing center hours are weird during spring term, so pay attention to that. The exam format is multiple choice. That you should not interpret from that it will be easy. Uh, it will be about 20 to 25 questions. It takes students on average an hour and a half to 2 hours, 2.5 hours, plus or minus, whatever margin of error you want to give yourself. If you've looked at the syllabus, we're just a little bit behind where I thought I'd be in terms of subject material. I can pretty well guarantee we will not get to chapter 4 prior to this exam, so you don't have to worry about the chapter 4 study guide and those problems yet. I guess those problems that are on the practice exam that are related to chapter 4, you can also delay. But you can go ahead and report that you've completed the practice exam at the appropriate deadline. I'll move the deadline for study guide 4 back accordingly. Let's see. Other questions you want to ask? The best way to prepare for the exam is to figure out which issues are challenging for you and then to work on them. This class is way more about what you can do than what you know. So be aware, because there's the very real possibility that you will feel more or less confident that you know the material, but if you haven't practiced enough, knowing the material will not be good enough. You have to have these skills. The example I use that I'm most familiar with is musical performance. However, if you've done athletic competition, you know this as well. I just don't have any good sports analogies. I'm sorry. So I play the organ in church, played it for years. My wife really loved it for me to play the organ while she was sitting with small children. In any case, they're starting to be grown and tolerable now, so it doesn't matter so much. But I got kind of cocky this past Christmas and decided I wanted to play an organ solo in sacrament meeting. And I chose something that was really probably beyond my capability. And though I thought with a lot of practice I could get there. And what I found in the past is that for something that's challenging, I have to practice it enough so by the time I'm performing, I'm no longer looking at or no longer needing to read each and every note. If I'm having to say, hold on, is that a B flat or a A sharp or what? Same note. Then I'm in trouble. And this Christmas, I actually crashed and burned spectacularly in front of the whole ward. I just started going too fast because I was nervous, and then my brain couldn't keep up with my hands, and it was just a disaster. So, on the other hand, I've also had times before where I really, really practiced, and by the time it came to perform, it wasn't that big of a deal because I had learned the skills and made them a part of me. That's kind of how you want to do things. You want to practice things that are hard for you enough that it's no longer difficult for you. And you should know going into the exam the exact kind of problems that you're going to struggle with. Okay, so end speech. All right, acid-base chemistry. We've dealt with two kinds of problems so far that you ought to be prepared to deal with. One is this base strong enough to deprotonate this acidic group? And go ahead.
Will there be TA review sessions?
Will there be TA review sessions? Aside from like let's see, they will continue to hold their regular recitation sections. I will ask them to, I will ask them to plan an exam review either to do during their recitation section or at another time. Okay. All right. So the question could be asked, is this particular base a strong enough base to remove some acidic proton? So to answer that question, it's really just as simple as writing out the equilibrium. You can try to memorize some rules. So, for example, a base can remove any proton whose pKa is less than the pKa of that base's conjugate acid, which is true, but you're going to get confused maybe. So alternatively, you can just take it slow, write out the equilibria, draw the acid, draw the base, then on the other side, draw the conjugate base of your acid and the conjugate acid of your base. Identify the acids on either side of the equations, look up their pKa's in the pKa table, make sure you get the right one. We need the pKa for the positively charged ammonium group and not the neutral amine. And then over on this side, the pKa of a thiol, if you looked at a pKa table, would be around 8. And then the strongest acid wins by losing its proton. And so the equilibrium goes in the direction of the weaker acid. So if I were to ask, is this particular base strong enough, sorry, I'm in a hurry, to deprotonate the ammonium ion? The answer is no. Okay? Practice that, but that's a fairly simple way of testing your knowledge of pKa stuff. More complicated is to ask the question, what is the formal charge on this molecule at pH 7? All right? And normally, you have to understand what I'm asking when I ask this kind of question. The situation is, you take a neutral molecule and you dissolve it in buffered aqueous solution. And usually buffers are in the range of 100 millimolar concentration, whereas your neutral molecule will be, in the end, something like maybe 0.01 millimolar concentration. Or we can even go up by a factor of 10 or even 100. So in this situation, the pH of the solution stays constant, and the protonation state of acidic groups can change depending on the pH. Sorry about penmanship. I got a C in penmanship in like second grade. And then I remember having to have a talk with my dad about how prices were more determined than that. And I attribute to that most of my issues in life. But anyway, I've clearly gotten over that, haven't I? All right, so you're dissolving, I'm drawing a neutral molecule because I don't want to give away which are the acids and which are the bases. And the situation is you're going to dissolve that neutral molecule in a buffer. That buffer has a certain pH, but there's plenty of hydronium around and plenty of hydroxide and plenty of water. So we can add protons to groups, we can take protons away. You need to then, so to determine what the final state of each of these groups is, you have to know how to apply the relevant pKa knowledge. Okay? So I would have a pKa table over here, and the information would look something like this. let's see what else I might have. I put this on there, pKa of 4, pKa of 8. Let's see, what else am I missing? Oh, that really strange group that you've never seen before. And there might be others, but this is good enough. Okay? So we'd have to go through, you don't have to memorize these pKa's, but you need to know how to use them. Some of these are quite easy. I just look here and I see, oh, okay, got that proton, and then I make the comparison between pH and pKa. And remember that we worked this out last time. Oops, I didn't want to undo. I can't even see what I undid. Oh, right. I want to just, instead of writing down the equation again, I'll just bring it over. We last time figured out this relationship between pH and pKa in dilute aqueous solution, where if the pH is lower than the pKa, the acidic form of that group dominates. If pH is higher than pKa, then the basic form dominates. So if I look at this side chain with the purple group on it that I have identified as an acid and its pKa is 4, but pH is 7, what that tells me is at physiological pH, at pH 7, this thing should be in its negatively charged conjugate base form. See that? Okay. That's probably the one of the easy ones. Similarly here, the sulfur thiol proton has a pKa of 8. pH is 7. 8 is greater than 7, so acid form dominates. At pH 7, it's still the neutral form. Same thing with the proton on this alcohol group. The pKa of an alcohol is 16, so at pH 7, this is still going to be the neutral alcohol. Now, these two are tricky and have tricked people before, and so I'm going to try to save you some points on the exam and save myself some time. It's in our mutual interest to figure this out now. So the problem is people look at this side chain and they say, okay, or they look at this group, they say, oh, that's an amine, so the relevant pKa is 38. And they will say, okay, well, at pH of 7, if the pKa were 38, at a pH of 7, you would expect that NH2 proton to still be on there, one of those NH2 protons, okay? And that's true. It actually is still on there. There's no, it doesn't get removed. But what they forget is that we're allowing the solution to influence the protonation state of these side chains. So not only do we have to worry about whether this pink proton can be removed, but we also have to worry about, so the pKa for going from, let me just try to draw it this way. The pKa from going from neutral amine to negatively charged amide is 38. But the pKa from going from positively charged ammonium group to the neutral amine is 11. So we're talking about a different proton here. Can't choose a color, wasting time. All right, so because we're in dilute aqueous solution and we can either add protons or take away protons based on the pH, we have to not only consider going from neutral amine to negatively charged amide, but we must also consider going from positively charged ammonium to neutral amine. All right? People ask, but that proton wasn't on there to begin with, so where did it come from? It came from the solution. Yeah.
Why doesn't the hydroxyl group turn to a water?
Why doesn't the hydroxyl group turn to a water? Good. So we could ask the same question here, and I'm going to write this in a slightly different way so you can see the equilibrium. The pKa of going from neutral water to negatively charged, or sorry, neutral alcohol to negatively charged alkoxide is 16. The pKa for going from positively charged, this actually is called an oxonium ion, to a neutral alcohol is -2. Sorry, so all right, so the pKa of -2 is relating to this proton being removed. The pKa of 16 is relating to this proton being removed. So we would say at pH 7, 16 is greater than 7, so we would expect the acid form here, the neutral alcohol, to dominate in the sense that we would have no alkoxide whatsoever. Now, comparing the equilibrium between positively charged oxonium ion and neutral alcohol, at pH 7, 7's -2 is much less than 7, and therefore the base, conjugate base form should dominate, and the conjugate base form is the neutral alcohol. Yeah?
So theoretically, if this is a pH -2.5, you would see that.
Right, if you could lower the pH that far, which generally doesn't happen in like biological contexts, but yeah, you could see the protonated form. The only reason we typically just forget about that and don't worry is because -2 is not really accessible physiologically. Yeah.
So I think that we compare the pH of the solution with the pKa of these groups.
Yeah.
But a lot of these are much greater than 14. Does that mean that they're, always deconated?
Sorry, much greater than 14?
14 is the maximum.
Oh, 14 is the maximum pH in water. Does that mean they are always, basically always have those groups on? Yes, in water, absolutely. Yeah, so, yeah. Though, yeah. You can remove protons from alcohol groups in biological contexts. Remember that as long as you have hydroxide, hydroxide should be able to deprotonate an alcohol.
It's not going to be an aqueous solution.
Well, yeah. But I guess I hadn't actually thought about that question about maximum pH, so I'm just sort of hedging a little bit. What I would say is that what I'm showing you is a peptide or a protein, and proteins, this is way far into 352 in biochemistry, but proteins fold and adopt interesting shapes, and if you can sequester side chains away from water into an active site, some of these environments change the pKa's, and then other protonation states become easier to get to. Not a huge issue now, but yeah.
So with this, just so I understand this example of the nitrogen, so at like pH 7, that's not something to worry about because both 11 and 38 are greater than 7.
So at pH 7, the negatively charged amide is not something to worry about. At pH 7, neither is the neutral amine. Yeah, so the form that dominates at pH 7 is that one. Yeah.
So if the pH was 12 or 11, would that mean it would be the ammonium that would dominate?
If the pH was 12, if pH is greater than pKa, then the log is negative and the base form dominates. So at pH 12, if pKa is 11, the neutral form would dominate.
Oh, that's not.
Yeah. Uh-huh. Go ahead.
So when asking questions like this, should we always consider like both the adding proton and subtracting proton, like ammonium,
Yes. So with the amine in questions like this, always consider adding the proton and subtracting the proton. if you forget about getting rid of this proton, you're going to be okay because we're never going to get to a pH above 38, right? But if you forget about this one, you're in trouble. With the alcohol side chains, if you forget about this one, you're probably okay because, again, we're never going to have a pH below -2. Maybe. I don't know. Yeah, so you can forget about this one. And frankly, you can probably forget about that one too. At physiological pH, yeah. All right, go ahead.
So basically, just looking at the possibility of protonating and deprotonating each one of these side chains.
That's right.
And then comparing to the pH of the solution to see which one is the dominant one.
That's right. Yeah, the question is we're considering protonating and deprotonating each of these side chains depending on what the pKa's are, and then comparing that to the pH and choosing the dominant form.
But then the greater, what is the overall trend that we're looking for?
What is the overall trend we're looking for? What I'm asking is for you to consider each side chain and then tell me what the overall charge on the molecule is.
Yeah. So then if the pH is greater than the...
If pH is greater than pKa, then the proton associated with that pKa is gone.
It's gone.
Yeah.
Okay. So then it takes its conjugate form as protein.
That's right.
Okay.
Okay. So lastly, the last side chain to consider is this neutral group. It's actually called a guanidine. And you don't find a pKa for the neutral guanidine there. It's probably known, but it's not relevant at physiological pH. It's probably high, like high up, kind of like it is for the amino group going to the negatively charged group. But instead, we have a pKa for the protonated form of the guanidine side chain. That functional group is actually called a Guanidinium Group. By the way, I'm using these words to facilitate discussion. They're not really words to memorize, but I will use them, and so as long as you're able to follow along. Guanidine is the neutral group here. Guanidinium is the positively charged version. That pKa is 12, and that's for one of those two protons. So at pH of 7, pKa is greater than 7, therefore the acidic form should dominate, and we expect to have the positively charged guanidinium form. Okay? All right. Yes?
Explain the last one more time. How it was positive, not.
Right. So if we look at this neutral group, we don't find that neutral group on our pKa table. Instead, we find its conjugate acid, right? So I'm going to draw its conjugate acid. I'm going to write out the pKa. Then I'm going to compare that pKa to the pH. 12 minus 7 is plus 5. That would mean that the acid form dominates. And so that would be positively charged. Okay, so I got to do that one by one, and then I got to be good at adding single-digit numbers, so, and or subtracting. So let's see, there's a plus 1 there, a plus 1 there, neutral, neutral. I'm going to just amend this because I decided halfway through to change how we were talking about these side chains. So pKa of 8, this form dominates. pH, pKa of 4, the negatively charged version dominates. All right, so going through, I've got plus, plus, neutral, neutral, minus. So overall formal charge is plus 1. Yeah.
So do we not, like the guanidine, we don't go to each ammonium group and determine its third?
Yeah. So that's one of the mistakes people make, and that mistake is related to looking at a pKa table and overgeneralizing. So we're going to learn in chapter 3 about things called functional groups. This guanidine is a different group than just an amino group. They have different properties. Part of the difference is the fact that the lone pairs on those nitrogens are resonance stabilized in at least these two. And so this isn't an isolated amine. It actually is involved with the other groups nearby. So yeah, I have had people make that mistake with the guanidine group before. They're like, oh, that's an amino group, even though they saw the full thing on the table. Yeah. So look at the functional group. Try to find the thing that matches the situation most directly. Go ahead.
So what's the overall FC for transfer functional?
Formal charge, sorry. I was abbreviating. Formal
That's
charge.
for the whole protein, correct?
That is for the whole protein, yes.
How do you get a +1 do?
A +1 here, a +1 there, a -1 there. Yep. Okay, one other mistake I've seen people make is when I draw out the structure of a short peptide, often I draw it as follows. A peptide is a polymer of amino acids. You'll learn more about this later. And so we can just draw it like this. Now, we've dealt with the side chains. Sometimes people get mixed up about these NH groups that are in the protein because they think, oh, I know what that is. That's an amino group. And again, I'm telling you, no, that's not. That's not an amino group. It's called an amide or peptide functional group. And the resonance stabilization of lone pairs on the nitrogens with the adjacent carbonyl group changes the amide nitrogen relative to just a regular amino nitrogen. So it turns out, if you look at the pKa table, you will not find amide protons on that pKa table. Because in general, the pKa for removing or adding a proton to the amide group are so outside the range of physiological pH that we don't worry about it. Okay, so I've had people make all kinds of mistakes because they're suddenly like, oh, right, that's just a neutral amine, therefore at physiological pH it should be protonated. Oh, 1, 2, 3, 4, 4 positive charges plus whatever else, and now I'm off by a huge amount.
So we disregard those.
So disregard the amide backbone. Yeah.
And that's just because it's part of that.
Well, it's because, do we disregard it just because it's part of the backbone? No, we disregard them because they're part of a functional group. It's not just a regular amino nitrogen, it's an amide nitrogen, and that nearby carbonyl group totally changes the chemistry, changes the pKa. Adding a proton here to getting to the positively charged group would have, that proton, if added, would have a pKa of lower than -2. And removing this proton would have a pKa that was also really quite high. Yeah.
But the other groups, we can see a little.
But other side chains, yes, we consider.
So what's different about that amide compared to the other groups?
Other,
The one
Yeah. How is that amide different from the other groups?
so you're asking about the difference between this functional group and these two? No.
You talked about the
1, 2, 3, 4, this one? It will be basic. This is also an amide. It just is that this nitrogen is attached to 2 hydrogens instead of 1. But its chemistry will be interchangeable. Yeah.
when you were talking about the amide, you would circle the one that was second from the left.
These are all amide bonds. Sorry. Yeah. Sorry about that. I didn't quite understand the question. These are all examples of amide functional groups. Yeah.
So just to clarify, for both the C terminus and the N terminus, there's endpoints we're not learning about carbonation states.
Well, so are we not worrying about protonation states and you're using terms called C-terminus and N-terminus? It actually depends on what the functional groups are. This is a little bit further than I think I want to go, but I will just say that I'm going to draw a small dipeptide. That means two amino acids adjacent to each other. And you can make these in such a way that you don't have an amide bond here or here. The pKa for a carboxylate that's in a peptide is a little bit lower than the normal pKa. You wouldn't be expected to memorize that. If you needed it, I would give it to you. The pKa for an ammonium group that's in a peptide in the backbone tends to be around 9. And so, yes, at physiological pH, you'd have a positively charged N-terminus and a negatively charged C-terminus. That's, I think, beyond the scope of where I want to go, but you just, same principle, you have to look at the functional groups. Yeah?
For instance, there's still like Amide and Amine groups that we can and can't disregard. Could you see an example of a chain that has one of each? One that we do worry about and one that we don't?
Sure.
How they would look different.
Okay, let me see. Dun, dun, dun. Haha, I'm really going to throw you for a loop on this one. So, evil. Okay. This is a molecule that's related to a peptide. You don't want to know this. It's called a diketopiazine. But the key points here is you've got an amide functional group. You've got another amide functional group. And at physiological pH, or pH ranges, maybe let's say from 2 to like, I don't know, 9, there are no relevant pKa's for the amide group. Any pKa's would be outside that, so I generally don't give them to you. So you can find those amide functional groups and ignore the lone pair on the nitrogen, and you can also ignore the proton on the nitrogen if it's there. Okay. In contrast, if I look at my pKa table, I can see this functional group here, which is a carboxylic acid. And actually, I mean, we're dipping into chapter 3 as we talk about functional groups. Carboxylic acid, and then this functional group is an amine. Notice the difference between an amine and an amide. The amine has a nitrogen bonded to 3 things with a lone pair on the nitrogen, and none of the things to which it is bonded are carbonyl groups. A carbonyl group, by the way, is a carbon doubly bonded to an oxygen. That's another functional group. Do you see the difference between the amine and the amide? And we haven't talked about this in a lot of detail, but the presence of this carbon-oxygen double bond adjacent to the nitrogen affects the chemistry of this group. The reason for that is the lone pairs on the nitrogen can be delocalized by resonance, and so they're less available for doing acid-base chemistry. Okay, so what would I do? Same as I've always done, same as we did above. pKa is 4, and that's for going to the negatively charged form. Okay. We would not worry about the pKa of 38 going to the negatively charged form. We can if we want to, but we must also worry about the pKa of going from positively charged ammonium form to neutral amine, and we would conclude at pH 7 that the ammonium form dominates and that the negatively charged carboxylate form dominates, and then you can answer the question. All right, yes?
What do you need to know about the functional groups for the test?
What do you need to know about the functional groups for the test? We'll
Memorize
talk about that when we get to chapter 3. Yep, which is like in, I don't know, 20 minutes. Okay. All right, so we've learned how to deal with pKa data, and that's an important part of science, is being able to use data to make predictions. The second thing we need to do with acid-base chemistry is really get a feel for understanding why things are the way they are. So we're going to explain some of the trends in the pKa values, and it won't take a long time, but you'll see some basic principles here that help explain why groups are more or less acidic than others. First principle is strong acids have really stable conjugate bases. Strong acids are strong because their conjugate base is stable with the electrons that are left behind after the proton gets removed. A related principle is that strong bases have really exceedingly weak conjugate acids. Another way of saying strong bases is reactive or unstable bases have really exceedingly weak conjugate acids. Okay, so let me illustrate this principle with just a few pKa's. HCl, pKa minus 9. I think, maybe 7, I forget. Doesn't matter. Okay, carboxylic acid, pKa 4. Water, pKa 16. Alkyne proton, pKa 25. Methyl proton, pKa 50. Okay, so strong acids have conjugate bases that are stable. Cl minus, conjugate base of the carboxylic acid is the negatively charged carboxylate. Conjugate base of water is hydroxide. Conjugate base of the alkyne is this negatively charged functional group. I'm going to call it an acetylide because that's what people call it, but you don't need to memorize that. And then the conjugate base of methane is just the methyl anion. All of these, do you see how all of these are what are left behind when we remove the acidic proton? Okay. So and this is just some of the molecules that are in your table in your text. With the low pKa's, we have strong acids. Then down here we have weak, and by that we mean exceedingly weak acids. And then the trend is reversed. We have strong bases, and then we have weak bases. This may change something that you learned in general chemistry. I think you may have learned something in general chemistry like, well, weak acids also have weak conjugate bases. That's true in this middling region where the pKa's are in the range of like 4 to 8. But we're dealing with organic compounds, and the range of pKa's is much more expansive than that. So methane, a hydrocarbon, is an exceedingly weak acid. The pKa is 50. That means if you put methane in water, nothing happens, worlds without end, through eternity and beyond. Never even once in the universe does methane lose its proton to water. Okay? That tells you that the corresponding conjugate base, methyl anion, is super reactive. We will actually use this as a reagent, not in 351, but in 352, and you will expect it to be highly reactive. You will also learn that it is a bad idea to use this reagent in water. Why? Because as soon as you put it in water, it removes a proton from water, and you've just found a very cheap way to make a very expensive reagent useless. Okay? So, so interestingly, we can use these pKa values not only to predict strong acids, but also to rationalize how reactive the conjugate base is. That's really useful because we're going to use a lot of these conjugate bases as reagents to do chemistry. So having a feel for their relative reactivity is important. All right, so with that in mind, let's look at some trends that we can explain. All right, I'm going to present some acids: HF, water, ammonia, and methane. These are the hydrogen versions of some of the hydrogen compounds of second row elements. I'm going to write their pKa's here: 50, 38, 16, 4. And now I'm going to draw their conjugate bases: methyl anion, amide anion, hydroxide anion, and fluoride anion. And you can either draw the lone pairs or not. As long as your formal charge is correct, you don't have to draw the lone pairs if you don't want to. Okay. Strongest acid, weakest acid. Which is the strongest base? Right, strongest base, weakest base. All right, now let's rationalize this. Why is HF more acidic than water? To do this, we draw the conjugate base, and then we look at differences in the stability of the conjugate base, and the question we're going to ask is, how well or how stable is the conjugate base with either a negative charge and or the lone pair that's left behind when the proton gets removed. In this case, they're one and the same, right? Because when the proton gets removed, we have a negative charge left, and that negative charge comes because of the lone pair that was left behind. Why might F minus be more stable than OH minus? Electronegativity trends, right? More electronegative. I'm going to abbreviate electronegative like that. Less electronegative. Okay. all of these trends follow the same direction, and they basically mean the same thing. Okay, fluoro is more electronegative than hydroxide, more electronegative than oxygen. Therefore, the negative charge is more stable on fluorine than on oxygen. Therefore, F minus is a weaker base than hydroxide. Therefore, HF is a stronger acid than water. Yeah. Does a complete valence on fluorine help at all too? Well, all of these have complete valences actually. Yep, so that's not the difference. Look for the difference. One other thing, because electronegativity is great, this principle that we use to stop further questions, right? Because we know sort of what electronegativity means in terms of that's how much an atom wants electrons. But atoms don't want anything. So we want to sort of understand what that means. Go ahead.
Wouldn't it also be because the further to the right you go in the periodic table,
Is this also related to the fact that the further right or left? Okay. The further left you go, atomic size gets smaller. So, but this is related to electronegativity. So, I don't know if you learned something called effective nuclear charge in general chemistry. The idea is as you add more positive charge to the nucleus, the valence electrons are held tighter. Each valence electron feels a greater nuclear charge. And so valence electrons are held tighter, closer to the nucleus, lower potential energy, and lower in energy. Go ahead. Another question? Did I see something? Yeah.
could it all just be broken down to charge and distance?
Yeah, you can break it down to charge and distance. Electrons, more electronegative elements have higher effective nuclear charge, are therefore smaller. Their electrons are therefore held lower in energy. Okay, so if we were to, now I mentioned something a couple of days ago, and some of you have been asking, let's look at the, how do lone pairs differ from each other in energy? If we wanted to ask, what are the relative energy levels of the highest occupied molecular orbitals of these groups? They're all lone pairs. How do you tell which one's more reactive? And the answer is this. If we look at energy and we plot the energy level of lone pairs on carbon versus nitrogen versus oxygen versus fluorine, we will see that a lone pair on carbon is much less stable than a lone pair on fluorine. Electronegativity literally means then is associated with a feeling a greater nuclear charge and being closer to the nucleus and therefore lower in energy. Now this is a highly useful principle because now we can say things like, if these were going to be nucleophiles, which would be better nucleophiles? Well, the ones with the higher energy electrons, right? So you predict OH minus is a better nucleophile than F minus, and that is in fact observed. Okay? So we're going to use pKa information to rationalize conjugate base stability, and then we're going to use conjugate base stability to think about whether groups are good nucleophiles or not. All right. I feel like that was a pretty good punchline. So why don't we take a break and we'll start back at the top of the hour.